Black holes are among the most fascinating and mysterious entities in our universe. Defined as regions in space where gravity is so intense that nothing, not even light, can escape, black holes challenge our understanding of physics, space, and time. The concept of surviving a fall into a black hole may seem like pure science fiction, but it raises interesting questions about the limits of human knowledge and the extremes of physical reality. When contemplating whether anything could survive falling into a black hole, we must consider what a black hole actually is, the nature of its gravitational pull, and how the laws of physics apply under such extreme conditions. Understanding this question requires exploring both scientific theories and the hypothetical implications of extreme environments beyond our current technological and observational limits. Moreover, black holes force us to question our conventional understanding of death and destruction in space, not just in terms of physical matter, but also in terms of energy, time, and even information. A black hole forms when a massive star collapses under its own gravity at the end of its life cycle. This collapse creates a singularity, a point of infinite density, surrounded by an event horizon, which is the point of no return. Once anything crosses this boundary, it cannot escape. The force of gravity becomes so immense that time and space themselves warp around it. According to Einstein's theory of general relativity, space, time is bent by mass and energy, and a black hole is essentially an area where space, time has curved in on itself infinitely. One of the main reasons survival seems impossible is the phenomenon known as spaghettification. As an object falls toward the singularity, the difference in gravitational pull between its top and bottom becomes so extreme that it is stretched into a thin, long strand, hence the nickname. For a human, this would be a catastrophic and fatal process. Near the event horizon of a stellar mass black hole, this stretching and compressing tidal forces would destroy any known matter almost instantly. Thus, from a classical physics standpoint, survival beyond the event horizon is practically impossible. However, theoretical physics offers some more nuanced insights that open the door, at least hypothetically, to survival under certain very specific conditions. If one were to fall into a supermassive black hole, such as those found at the centers of galaxies, the tidal forces at the event horizon would be much weaker than those of a stellar mass black hole. This is because supermassive black holes have much larger radii. In theory, it might be possible for an object or person to pass through the event horizon of such a black hole without immediately being torn apart. That said, this survival would be extremely brief and ultimately meaningless from a physical standpoint, because once inside the event horizon, all paths, both in space and time, lead toward the singularity. Eventually, spaghettification would still occur. Moreover, due to time dilation or relativistic effect, while an outside observer would see the person slowing down as they approach the event horizon, from the falling person's perspective, they would fall right through with no noticeable change at that moment. Some physicists have even proposed that time effectively stops at the event horizon from an external viewpoint, but for the falling object, time continues as normal until its fate is sealed at the singularity. So while survival past the event horizon might be momentarily possible in the case of supermassive black holes, it would not lead to an escape or return. Quantum theory, however, brings an additional layer of complexity to the conversation. One of the most intriguing theories is related to Hawking radiation, proposed by physicist Stephen Hawking. According to quantum mechanics, black holes are not entirely black. They can emit radiation due to quantum effects near the event horizon, leading to the gradual loss of mass and eventual evaporation of the black hole. This raises the so-called information paradox. If black holes can evaporate, what happens to the information about the matter that fell into them? Quantum mechanics states that information cannot be destroyed, while general relativity suggests that it vanishes into the singularity. This contradiction implies that our understanding of black holes is incomplete. Some theories propose that black holes might be gateways to other parts of the universe or even to other universes, wormholes, for instance. In such a scenario, it is theoretically possible that something could survive the journey by passing through a wormhole created by a black hole, although there is no experimental or observational evidence to support this. Furthermore, the conditions required for a stable wormhole would demand forms of matter and energy that we have never observed, such as negative energy or exotic matter. These ideas remain largely in the domain of speculative physics, but they serve to highlight how little we truly understand about the nature of gravity and quantum mechanics at extreme scales. In recent years, advancements in observational astronomy particularly through projects like the Event Horizon Telescope (EHT), have allowed us to capture the first images of black holes, offering real-world glimpses into what was once only theoretical. These breakthroughs help validate many of Einstein's predictions, but they also underscore how much we still don't know. For example, some researchers now suggest that black holes might not have true singularities at all, but instead contain highly dense cores governed by yet unknown laws of quantum gravity. If this were the case, the notion of survival could take on a new meaning, not in the sense of physical escape, but perhaps in the retention or transformation of information. Could consciousness, or the essence of identity, survive in some abstract form? While this idea remains highly speculative, it is increasingly being discussed in the context of simulations, quantum computing, and even theories of holographic reality. Whether or not these ideas hold scientific merit, they reflect a growing willingness in the scientific community to push the boundaries of what we consider possible. Ultimately, the question of survival inside a black hole touches not just on astrophysics, but also on the philosophical and speculative limits of science. In our current scientific framework, survival inside a black hole appears impossible. The laws of physics as we know them break down at the singularity, and no technology or biological entity could withstand the extremes of gravity, radiation, and time distortion. However, black holes are also indicators of where our current understanding fails, especially the contradiction between general relativity and quantum mechanics. They are natural laboratories for testing the limits of our theories and future discoveries. Perhaps involving quantum gravity or a successful unification of physics may reshape our views. Until then, the idea of surviving a black hole remains a compelling blend of science, theory, and imagination. It invites us not only to explore the furthest reaches of space, but also to confront the deepest mysteries of existence, knowledge, and reality itself. The more we learn about black holes, the more they reveal themselves as cosmic paradoxes, places where science meets the unknown and where the impossible might one day become possible.